Okay, good evening, everyone. My name is Jay Walsh. I'm the Vice President for Research for the university. That is Northwestern University, where some of us wear purple once in a while. So to all of you in the room, welcome to this fantastic event, the CIERA Roundtable this evening. And then we're also live streaming this. So for those of you who are online, welcome to those of you as well. Tonight is about providing you, the community, with an opportunity to hear from and engage with in a conversation with a truly phenomenal group of astronomers who were deeply engaged in the most recent discoveries in astronomy by LIGO, which you'll hear about in a few minutes from the first speaker. So LIGO is the Laser Interferometric Gravitational Wave Observatory. That's a mouthful. So somewhere in there, there's a laser that looks at distances between things. That's what an interferometer does. We have a few experts in the room. I won't point to anybody in particular, who know a lot about interferometers, and the idea was to use those to detect gravitational waves. LIGO took decades to plan and build, and the discoveries that it would make and the theories that it would hopefully prove or not also were very much anticipated that those discoveries and the theories would line up, and we're going to hear a little bit more about that today. There's certainly this whole gravitational wave observatory has led to some significantly interesting results and frankly just awe-inspiring. I'm not going to talk about those. I'm going to let Shane Larson, who will be the first speaker, say more about those discoveries in a few minutes. And then he's going to introduce our panelists, who are up here in the front row, as well as our moderator, Michelle Larson, who's sitting right here in the front row as well, who's the president and CEO of the Adler Planetarium. So before I turn the microphone over to Shane, first of all, Michelle, welcome. We're delighted and honored to have you here as the moderator for this panel. The relationship between Northwestern and Adler Planetarium has been growing through the last several years, and we're just delighted with that growth and really delighted that you're here tonight. CIERA, before I go too much further along, is the Center for Interdisciplinary Research in Astronomy. And I always forget the exploration and never remember whether it's education or exploration, so I just had to look that up. It's one of our 50-ish research centers at the university. So universities are largely organized as a university with schools and departments, and then there are these units that span the entire university, and we have about 50 of these that are multidisciplinary, of which CIERA is one of them. This allows faculty from a variety of different components within the university, from many different departments, to collaborate, and there are organizational structures that allow that to happen. So within CIERA, and the reason I really have this piece of paper, is to indicate the departments that CIERA has. Faculty from physics and astronomy, earth and planetary sciences, statistics, electrical engineering and computer science, material science, applied math, mechanical engineering, chemical and biological engineering, obstetrics and gynecology, the learning sciences, chemistry, medical humanities, and bioethics. An incredibly diverse group of faculty participate in the astronomy center that is CIERA. So there have been, since CIERA was founded in September of 2009, there have been 19 different faculty who have served as principal investigators on grants that flow through CIERA. There have been more than 5,000 kindergarten through 12th grade students and more than 500 teachers of those students at over 200 schools who have been inspired and educated by talks given by CIERA faculty. There have been more than 23,000 attendees at more than 130 CIERA events in the past 8 years. It is a phenomenal success that we have had with CIERA, and much of that goes to the talented faculty who started this. CIERA was started by Vicky Kalogera, David Meyer, and Fred Razio. It's now directed by Vicky, and has had, just as I said, phenomenal success through these years. And you will hear about one of the successes tonight, one that has gathered quite a bit of, as you know, national and international attention. So, as an introduction to our first speaker, Shane Larson is the Associate Director of CIERA, and he's a Research Associate Professor at Northwestern University in the Department of Physics and Astronomy. He's also an astronomer at the Adler Planetarium. He earned his master's and doctoral degree in physics from Montana State University. His research interests include, big surprise, gravitational waves, as well as data analysis and a variety of other cosmological events like binary star evolution and gravitational dynamics in extraplanetary systems. He has an incredible passion and knack for public communication of relatively challenging physics and astronomy. So with that, I will now turn the microphone over to Shane Larson.
Okay, well, thank you, Jay, for that kind introduction, and thank all of you for being here tonight for this very special celebration of what truly has been a remarkable and momentous event in the history of astronomy. When you become a professional astronomer and astrophysicist, you often imagine that you will live to see really transformative events in astronomy, things that literally change our understanding of the cosmos and the universe. And I have to say, I never expected to not only witness such changes, but to be part of it. And this has been the most exciting thing that has happened certainly in my career these last few months. And it's very gratifying to know that the work done by our students and our postdocs and our faculty here at Northwestern really is so close to the frontier that there's no way we couldn't have been part of this great discovery. And so what we're going to do today is I'm going to spend this first 10 minutes or so chatting with you about the discovery, about what it was. I'm going to tell you the story to kind of get everyone on the same page, give everyone a little bit of vocabulary, and then we'll have our panelists, our 3 faculty members, come up, and there will be a little moderated discussion and a chance for you to ask questions about the things that you've heard and the things that interest you the most about this event. Okay? Okay, so if I can get my lights off there so we can see the slides. So anytime you open up a magazine or a book or you see a news story about the latest, greatest discovery in astronomy, invariably you will see pictures not unlike the ones on the screen behind me. All of us have grown up in an era where access to beautiful, robust astronomical images like these are easy to access and are so familiar to all of us that virtually no one can look at a slide like this and not see something that they recognize. This is really how astronomy has been done for the last 400 years. We've been using telescopes, which are mechanical extensions of our eyes, to look at things that are so impossibly far away from the Earth that no person in this room or in the foreseeable future will ever be able to go there. When you look at a slide like this, nothing on here is accessible to individual humans, except maybe the moon. But we haven't been to the moon in almost 50 years. Everything that we learn about astronomy and that we think we know about astronomy has been gleaned by measuring signals that come to us from these enormous distances. We gather them up, we look at them, we study them, we ponder them, and eventually we come to some understanding about how the universe works. And for 400 years, we've more or less only been doing that with telescopes. But as it turns out, there are other signals that come to us from the cosmos. And about 100 years ago, Albert Einstein suggested that maybe another way to understand the universe would be to not use light as a probe, but to try and detect the gravity from distant astrophysical systems. As those systems move and evolve in time, they warp and stretch and pucker the space-time around them. That information, that change in the gravitational field, propagates across the universe and eventually washes across the shores of Earth. 100 years after Einstein had that spectacular idea, an idea that he was not certain we would ever be able to make good on, we have built a machine capable of detecting the faint gravity from distant astrophysical systems. We call it LIGO, the Laser Interferometer Gravitational Wave Observatory. There are 2 of them here in the United States. This one in this slide is outside Hanford, Washington. It has a twin outside Livingston, Louisiana. And on the 17th of August this year, sometime in the early morning, a gravitational wave signal washed across LIGO. Now, this is brand new astronomy, but already we've made 5 gravitational wave detections. So we're a little bit jaded, and we're like, oh yeah, another gravitational wave signal, no problem. Okay? But what makes this discovery so exciting is that 1.7 seconds after LIGO and our companion Virgo in Europe detected that signal, our colleagues who study the sky using a kind of high-energy light called gamma rays, they have a satellite in orbit called Fermi, also detected a signal. And that was truly the momentous event that happened. We have been anticipating for decades the opportunity to study something in the cosmos, both with gravity and light at the same time. And the moment we realized that it had happened, the worldwide astronomical community mobilized in an effort to try and figure out if we could see this thing with light after we'd detected it in gravitational waves. And indeed, that's what happened. This is what our data looks like. Now, most of you grew up looking at pictures from the Hubble Space Telescope. But when you're a professional astronomer, this is what you stare at every day. And when I see LIGO data that looks like this, and I see that long, sinuous swoop of a signal across there, I get really excited because I know what it is, I know what it means, and I know I'm going to have a lot of work to do for the next few months. Okay? In a similar way, this is what the gamma ray data looks like. The gamma ray folks are just counting gamma rays in their satellite, but when they see this big bump up like this, they get really excited because they know something happened. Okay? And it's the proximity in time, less than 2 seconds, of this signal and this signal that started the story that you're going to hear about tonight. So what was it? What LIGO told us is that the source was a pair of neutron stars orbiting around each other. Neutron stars are the skeletons of dead stars. They are locked together in an orbit still, even after their parent stars died. And they're going around each other about 10 times every second at the moment that LIGO detected them. They're separated by about 400 kilometers. And as they emit these gravitational waves that LIGO was detecting, the orbit shrinks. And as it shrinks, the neutron stars go around each other faster and faster and faster. There's nothing to see except the gravitational waves, but we can tell what's going on. As the neutron stars get close together, they become sensitive to each other's strong gravitational field. It distorts them until they merge and become one object. And in that titanic merger, it creates the first signal in light that we detected here on Earth, that gamma ray burst that Fermi detected. It also throws out a cloud of material from the collision of the stars that expands out. It's very hot, very energetic, it's very dense. As it cools and expands, it forms new elements. It also emits light. And over the course of the next many months, we're still looking at this source today, all of this material, and including the ejected gamma ray jet, the burst, begins to descend in energy. It begins to cool. It emits gamma rays, and then X-rays, and then ultraviolet light, and optical light, and infrared light, and radio waves, all the way down. And still today, 2 weeks later, many months later, sorry, the initial 2 weeks was what we observed, many months later, we are still studying this object. But that's the whole story. There's about 100 seconds of gravitational wave data, and then there's no gravitational wave data. And then there are many months of data in the form of light, but eventually this is going to fade away, and we'll never see it ever again. Okay? So, These neutron stars are exotic objects, and this is why we care about this. They are the skeletons that form when a star explodes and dies. You can also form black holes, but neutron stars are far and away more common. Okay, they're about the size of a city, so you can see it hanging over the Chicago skyline there. If you could stand on top of the Willis Tower with a spoon and reach up to that neutron star and scoop up a spoonful of it, the mass of that sugar cube-sized bit of neutron star material would weigh 30 times more than the entire human race. Maybe a little bit more after Thanksgiving dinner. Okay? These are exotic objects. They are things that we absolutely cannot understand by studying them here on Earth in the laboratory. The only way to understand them is through the science of astronomy. And their story and their evolution is intimately tied into our story of where we came from and where everything we see in the world around us came from. So what does the data from these things look like? This is very typical gravitational wave data. Here's the 5 ho-hum sources that we had seen already. They're all black holes. But on the bottom there, you'll see the signal from the neutron star. Now, I'm a gravitational wave astronomer, and I can tell what's going on. I'm really excited about this. And you're like, wow, painful flashbacks to my physics class. Okay? Waves. These are waves, just like waves that you've been exposed to before. And the problem that we have as gravitational wave astronomers is how do we convince you that there's astronomy in that? The truth is there is astronomy in that. What you're looking at from the neutron stars is different than what's there from the black holes we saw before. That's how we know they're neutron stars. But it's still not very exciting for you to stare at them, but they are indeed waves. And just like I can take the light from a telescope and turn it into a picture, I can take the data from a gravitational wave signal and turn it into a sound. Can you hear it? That is the orbit of the 2 neutron stars getting smaller and smaller and smaller, faster and faster and faster, until they collide at 1/3 the speed of light. Okay? That is the data turned into sound in the same way that data from a telescope is turned into a picture. LIGO spent the first day localizing where that thing was on the sky. We figured it was neutron stars, and there should be light because we saw the gamma ray burst. And by the end of that first day, our colleagues with telescopes around the world, and you'll hear a bit of this story after I'm done, had localized which galaxy it was from. This is that galaxy. It's a small, nondescript galaxy in the constellation Hydra called NGC 4993. It's kind of a ball of a galaxy. It's not pretty and disc-shaped like the Milky Way. But right there in the halo, on the outer edge of the galaxy, there's a bright spot that wasn't there before. And that bright spot is the remains, the ejected light and material glowing softly, fading away after the collision of those 2 neutron stars. So we've been staring at that. In the first 2 weeks, about 70 observatories around the world imaged and studied this in great detail. The source went behind the sun, and our friends who do radio astronomy were the only ones who could see it for a long time. And now it's emerging again, and we're back to staring at it with other telescopes as well. Okay, so that's the story. That's what you're going to hear about. You'll hear about the things that we did to discover it, the things that we've done to analyze it and understand it. Okay, and you'll have a chance to ask some questions. I always like to leave you with something to go see on your own. There isn't a lot written about multi-messenger astronomy yet. Okay, but there's a lot written about gravitational waves. So these are 2 fantastic books about LIGO, black holes, and neutron stars and gravitational waves, which you can see. If you'd like to work on gravitational waves with us, this is a citizen science project that we lead out of Northwestern called Gravity Spy. Okay, you can help us look at LIGO data. And then here's a series of blog posts and video links to things we've produced at Northwestern and also that LIGO and Virgo maintain. And there's a lot of the multi-messenger gravitational wave plus EM stuff there as well that you can study on your own afterwards. Okay? If you go look at all of that stuff and you're still confused, you know where to find us. Okay? Okay. I'm going to hand it over to our panelists. So I'd like to introduce Michelle Larson from the Adler Planetarium. She's the president and CEO, and she'll introduce our panelists. So thank you all for your attention, and we'll have a little bit more of a conversation.
All right, Shane did a great job at setting the stage there and teasing us just a little bit. And now we have 3 scientists who have worked on this project along with Shane, and they're going to help us understand a little bit more. So thanks for being here. I'll first introduce them, and then I'll take a seat and we'll moderate a conversation and for about 20 minutes, and then we'll have 20 minutes at the end for you all to ask questions as well. So first, down here on the end, we have, as you heard, the director of CIERA, Vicky Kalogera. Vicky is all of these faculty are faculty in the Department of Physics and Astronomy, so I wanted to say that up front so I don't have to repeat it every time. So Vicky is the Daniel I. Linzer Distinguished University Professor in the Department of Physics and Astronomy. She's the lead astrophysicist on the LIGO scientific collaboration that made the gravitational wave detection that you heard about. Vicky's an expert in black hole and neutron star formation in binary systems and in LIGO data analysis. She's been a member of the LIGO scientific collaboration for more than 15 years. Next to Vicky, we have Wen-fai Fong. And Wen-fai is a new faculty member at Northwestern. She joined us this fall in 18. She's an assistant professor in the department. She spent the past few years planning for this electromagnetic follow-up, so that's very foresightful of you. And so was ready to go when this happened. She works to understand the mysteries of cosmic explosions and their environments through observations across the entire electromagnetic spectrum. And next to Wen-fai is Raffaella Margutti. And Raffaella is an assistant professor in the department. She's been working for more than a decade in the field of astronomical transients, including the most powerful stellar explosions in the universe and the disruption of stars by supermassive black holes, all events that emit these kind of strong signals. Her investigative tools consist of astronomical observatories, both on the ground and in space, and they also span the entire electromagnetic spectrum. So before you hear today, you have experts in gravitational wave astronomy and the entire electromagnetic spectrum of follow-up, and that's the conversation that we're going to have. Besides the people you see in front of you, the LIGO group here at Northwestern is much larger than that, including a number of graduate students and postdocs, and many of them are in the room today. So if you could just stand if you're a graduate student or postdoc on LIGO, it'd be great for people to see that you also contributed to these great discoveries. Thank you. It takes a village to do this kind of science, that's for sure. To get started, I thought we would play off of a few of the very evocative words that Shane said that I think you can give us some more insight into. In particular, when he said that the entire astronomical community was mobilized by these 100 seconds of gravitational wave observations that then led to the EM follow-up. So Vicky, I thought we'd start with you talking about what those early moments were like when it was the gravitational wave discovery and when it was all starting to come together. Tell us about that day.
So I was actually in Utah. I was on a family vacation. I had a 1-week planned vacation. And in fact, I had promised my family that I would stay offline completely. And had I kept my promise, I wouldn't know the signal had arrived, but of course I don't keep my promises. So especially when it comes to staying offline. So I woke up in Utah and the signal arrived around 7 a.m. Eastern time. So in fact, what I had planned for my day that day was that my husband, we were in Moab, Utah. It was the desert. We had come from the mountains in Colorado. And the kids were going to go with my husband to a hike in the desert. And I said, I'm not hiking in the desert. I'm going to stay at the spa. And you, my dears, can go hiking at 100 degrees. And after they left the room, I thought I will check my email. And then I saw the news. Then I saw the news of the discovery. I told this story to Dennis Overby, the science writer at New York Times. And then he wrote, Vicky Kalogera was hiking in Utah. And my husband saw it and said, really? Anyhow, long story short. So I saw the emails, and of course I canceled everything. And from that moment up until our announcement, basically I worked for the long 2 months.
What did it take to get ready for letting the electromagnetic astronomers know that they should mobilize?
So
how does that happen?
So what it takes is for us to analyze the data and figure out roughly where on the sky is the source. So localization, Shane said the word, localization is the first thing. So we have to analyze the data, and the first thing we knew immediately, 100 seconds is a long gravitational signal. The black holes were all 0.2 seconds, half a second, 2 seconds. So long signal, we knew it was neutron stars. Neutron stars means light is going to come out of this collision. So we knew it was really critical. We tell our electromagnetic partners. So we had to localize quickly. And we localized first, big arc on the sky. We let everybody know through electronic means, basically a telegram system we have within the astronomy community. And then we had a few hours to to work on our data, the gravitational wave data, more and more, and improve the localization on the sky. And they can tell the story from their side, but what we knew already in those early morning hours is that the source was in the southern part of the sky. And it was morning here, but also still morning in Chile, in the southern part of the Earth, and the sky where you could see the source, but you couldn't see the source because it was the day. So yes, the event was there, and if it was the night, we could point the telescopes, but we couldn't. So we had a few hours to wait, and that allowed us to make the localization better. And it allowed them to prepare a little bit better.
Great, so lots of time spent trying to pinpoint exactly where, when they were ready, when nighttime came. And a critical piece of that story is that gravitational waves do not care if it's day or night. Gravitational waves go right through the Earth, right through everything, and so you will see them anywhere. Go ahead.
So we get to work 24 hours.
No, again, let's not go that way. Okay, great, thank you for that. So once LIGO was able to pinpoint, then Raffaella, why don't you tell us what then happened in your world of the EM follow-up, and then we'll get to Wen-fai.
Yeah, so it was morning, we got the alert about this new trigger in the sky, and we thought, it's gonna be one of these poorly localized LIGO events, so maybe let's wait a little bit. and then they sent us a better localization, and then we started planning because their localizations, they're good, but on astronomical terms, they're huge. They tell you something happened here. And
we're out there.
So we have to tile the fields with our telescope. So we really had to get ready. And I kept telling Vicky, give me the best localization that you have.
We were texting.
Work hard.
So waiting and tiling while she's trying to give you a better localization, but you're working in parallel, basically, at that. Wen-fai, similar?
Yeah, and I think one of the key points of their localization was that it was basically right next to the setting sun. So not only was, gravitational waves don't care if it's day or night, and so it could be that the localization is up when the sun is up, but luckily the sun just set, and then we had our telescopes ready in Chile. So Raffaella and I are part of a program that used a telescope in Chile to actually observe this. So luckily the sun just set, and just as the sky was getting a little bit dark, we started taking images right away. So it was a really exciting endeavor, but consequently we only had maybe an hour of time right after the sunset to take images. So it was a really, truly exciting but frantic.
Because then the source set as well.
Right, exactly.
Yeah. So there was a brief amount of time to get information from the source.
If I can add one thing, I remember texting Raffaella. So I was working inside the collaboration, but I knew Raffaella was on one of the key teams that had access to one of the telescopes that could tile the full region that we were providing to them. And I remember asking Raffaella, what's your cutoff time? How late can we give you information that is still useful for your team to plan ahead and then have the best information to find if there is a source, electromagnetic source. So she gave me a cutoff time, and then I went to the LIGO collaboration, and I said, you know, this is our cutoff time. Now we have to work as fast as we can and provide the best localization by that cutoff time.
Yeah. Way to drive things. There you go. I think a question that's burning in my mind, so if you'll let me take this prerogative, is we know you were planning to be at the spa that day and that got co-opted. We know LIGO is on all the time when it's running looking for gravitational waves, but we also understand that telescopes are heavily scheduled and there's a lot to look at in the sky, and so telescopes are scheduled all the time. So I have to ask the question is, what were these telescopes planning to do that night, and how did you drop everything and get to do this? Was there some protocol for that?
Yeah, so our programs are rated high enough that we can override.
This woman has a lot of power.
Yeah.
That's it.
Yeah, we're
You have
not,
override power
we're not
too.
beneath offering bribes. Or but yeah, we have these special types of programs where we can say, oh, we know that a neutron star merger is going to happen, or we hope it's going to happen. So when that moment happens, it's a very time-sensitive endeavor. So we basically take over the telescopes, but not without the permission of the people running those telescopes.
Yeah, you have to have some social skills. So.
Yeah, you do.
I was going to ask if you sent brownies or flowers to those that were supposed to be observing that night to make up for it. So,
yeah. And I think one of the biggest things is just making those observers feel included, and they were super excited and to be part of this discovery as well. So we had a remote takeover of the telescope in Chile.
A remote takeover, so you weren't there at the telescope.
Right, yeah. Yeah, we didn't have enough time to fly down to Chile.
So you just were here in Evanston?
Mm-hmm. Yeah.
So that's another, all of these telescopes are operated from afar. They can be operated remotely, and it allows for this kind of takeover when something happens.
Right, right.
Yeah.
I was actually in Montana also getting ready for a vacation where I was actually right before the eclipse. So this happened August 17th. The eclipse was August 21st, I think.
Yep.
And so actually the entire astronomical and gravitational wave community were preparing their eclipse trips, and a lot of vacations were canceled. So, over this event. So, but personally for me, I had no lodging plan except a tent in the middle of Montana. So, so I prayed that I wouldn't get eaten by bears for 3 days, and then came back and was able to get back and ready to work.
That's a great story. All right, way to avoid the bears.
Yeah.
I want to talk a little bit about, now that we have had this event that has mobilized the entire astronomical community, now that includes gravitational waves and the full electromagnetic spectrum, what more have we learned? What more do we now know about two neutron star mergers than we knew before? And help piece that together for us. So let's go this way. Raffaella, you want to start there?
Okay. So one of the things that we learned is how the universe forms the heavy elements. So anything that is heavier than iron. So we usually say gold because people seem to care more about gold. Yeah. So heavy elements in our universe, now we know that they are formed during these mergers of stars. And that is actually very relevant for our own existence as well. So this is one thing.
We're in a chemistry classroom, so we might as well point that out. We all remember from chemistry, it takes a lot of energy to push heavy elements together, and so regular burning stars don't have enough energy in their normal cycle to get things past iron pushed together. It takes more energy to put them together than you get out of it. But this type of a cataclysmic event puts enough energy into the system to now start slamming things together past iron. So that's how we get these heavy elements.
Anything past iron over there, so number 27 more, all of those are coming from neutron star mergers. That is what we know right now. So I think it's extremely
So the
relevant.
whole bottom of that chart, we now know where it comes from. That's fantastic.
That was a huge question mark that we had before.
Great, huge question mark. That's what science is about, and this is fun when we learn it. Wen-fai?
Yeah, I think this event had many firsts associated with it. It's really, one of the pinnacles, I think, in astronomy that will be written about in textbooks, high school textbooks and college textbooks for a really long time. I think that's really exciting. One of the things I think was most exciting about this event was that we found a Gammaray burst in association with a gravitational wave signal. So that slide that Shane showed where you see this kind of uptick, or what do you call it, chirp signal in gravitational waves, and then followed by this intense flash of gamma rays. So gamma rays are the most energetic form of light that we're able to detect. And these gamma ray bursts have actually been detected for a really long time, dating back to the 1960s. And this special class of very short flashes, these short duration gamma ray bursts that we saw in conjunction with this gravitational wave signal, we actually never had direct evidence of what their origin was in the universe, but we saw them once a month or so, for the past 20 or so years from gamma ray satellites. So I think now that we see something LIGO telling us there's a neutron star merger, and then followed by gamma ray bursts, it really solves this 40-year-old puzzle of what these intense flashes of gamma rays are from.
That's fantastic. I think it was Rutherford that said that astronomy is like stamp collecting, because there's a lot of observing and classifying. And so for decades, we've been seeing gamma ray bursts and making catalogs of them and picture books of them and family albums of them, and putting them together with light characteristics. We've been doing this for decades, and for many had no idea what caused them, right? But we knew it was important to keep observing them and to keep classifying them, and that eventually we would observe enough to understand what they were. And as you're saying, this is the key that finally identified that these short ones were two neutron stars together. So we can check off that stamp collecting album and say we know where these came from. That's great. Vicky?
So I want to comment from the gravitational wave side alone. It's the first time we actually observed directly the merger of two neutron stars. So this kind of phenomenon had never seen before, knowing that it is two neutron stars coming together. So that's a first. And it's a first because of course, we had seen the gamma ray burst, and even we had seen signatures or hints of the formation of the heavy elements. We couldn't prove fully this is what we were seeing, but we had the hints. Now, for the first time, we have, through gravitational waves, the proof that it is, in fact, two neutron stars. And the reason we have the proof is that only through gravitational waves you can measure the masses. Okay, so the mass measurement comes from the gravitational waves. The phenomenal thing that I'll make a personal remark in the following sense. I am a theoretical astrophysicist and not an observational astrophysicist as Raffaella and Wen-fai are originally. And in that sense, I grew up making predictions for what the data will reveal one day. And people in a different field than mine made predictions about neutron star mergers colliding and forming a gamma ray burst, and made predictions about neutron stars colliding and forming heavy elements. And these observations, these electromagnetic observations, are now the proof. So it's in a way a triumph of observational experimental astronomy coming together with theoretical predictions over many decades and providing the proof of a lot of predictions. And I think that is quite stunning. Often we find excitement into disproving theories. Well, this one event so far has proven a lot of theoretical predictions. And I find this quite satisfying, given that my upbringing in science comes from theoretical astrophysics.
And in that sense, it sets a new future, because
Yes.
from now going forward, we will have both eyes on the universe, all of the light that we can collect, as well as now adding the gravitational waves. So it starts a new era.
That gives us more information and new information.
Yeah, great. One last question, and then we'll turn the time over to the audience to ask some questions. I'd like to talk about this upheaval that has happened in gravitational wave physics first, when the first gravitational wave announcement was made in February of 2016. There was a drop everything upheaval for 6 months while the LIGO collaboration was working hard to eat at their desks and skip their vacations and verify the data and make the first announcement. And just when those email numbers were getting down under the thousands and life was getting back to normal, then this EM detection happened, and now you two got to join in on the drop everything and don't get eaten by a bear and make sure that you have Wi-Fi signal. that's likely not sustainable, that we can do this to ourselves as scientists all the time. So give me, each of you, some thoughts on where this may evolve. What does this look like as these become not mundane, but what does the steady state look like for multi-messenger astronomy? How are we going to deal with these kinds of things? And Wen-fai, why don't you start this one?
Yeah, I think, this really is a nascent field of observation, at least on the electromagnetic side. We've, as Vicky noted, we've been making predictions, or the community has been making predictions for the past several decades, and now we're starting to have these observations. And yes, it's definitely, having lived through the past 2 or 3 months, it's definitely not sustainable to do it all at once. I think really what struck me the most was kind of the teamwork involved across the entire astronomical community. So we had people from kind of all different backgrounds, not necessarily in gamma-ray burst science or neutron star merger science, but everyone studying explosions or the galaxies, kind of gathering together to observe this event. And I think the steady state it's really a great way to attract larger groups and big students. So for me, I actually just moved to Evanston 4 days before this event happened to start this new job. And so it's really an exciting time to be able to tell students, not just we're planning for this era, but this era is here, and now you can come work and observe. So I think really teamwork is how I view the steady state.
More help.
More help.
More help.
Yes.
Great.
Yes.
Vicky?
So if this were the first gravitational wave discovery, I would probably not have an answer for you. Because when the first time we discovered the 2 binary black holes and we lived through those crazy few months where we lived through something unsustainable, I didn't know how are we going to do this? How are we going to keep doing this? But then somehow we did it. I'm looking at Shane. We now have announced 6 binary black holes, and by the time the 6th came, which by the way, the 5th we announced, but the 6th event, it's a bit of, the order is a bit complicated. But by the time, let's say, the 6th came, it was 3 days before the 2 neutron star signal came. In the 1 week I was taking a vacation. 3 days before. And it was like, yeah, we got a binary black hole signal. Yeah, I have some work to do. It's OK. But we can go out to dinner. So by the time it was the 6th binary black hole, we could do it. It was sustainable. It had become sustainable. But if you asked me that question 1 month or 2 months after the first announcement, I would look at you in panic and say, I don't know how we're going to do it.
Okay. It didn't feel like it at the time.
It didn't feel like it was going to be sustainable.
So more help,
somehow we're going to do it.
perspective, right?
Perspective.
So more help, perspective.
Exactly.
What do you want to add to that storyline?
I like to remark that this event is not over. It's still going strong.
Very good point. It just came out from behind the sun.
Yes, it's going to come out on December 1st. And so actually, I look at my next 20 days, and maybe I'll answer to you after.
You don't have perspective yet. You're still in the first one. That's a good answer. That's a good answer. So our hope is that soon the electromagnetic partnership to the gravitational wave 2 becomes sustainable and mundane. But right now, you're still in your first one. Yes, that's a very good point.
Yes.
That was good. Excellent. Well, thank you all for that conversation. We're going to have Zach and Cody are going to stand in the aisles with microphones. And so if you have a question, we ask that you come to the aisle and line up next to them, and we'll just alternate back and forth. We're sorry to make you move, but that steps on fewer toes than if we move in between all of you trying to get you the microphone. So we'll just take questions if you want to come to the microphone or if you want to go up to them. Please don't. Just come and line up in the aisle right next to them. Go ahead, over here.
Hi. Thank you. The gravitational waves and the light waves are traveling at the same velocity. Why is there 1.7 seconds difference?
You were listening.
Who's going to get this one?
You go ahead, or whoever.
I get this one? OK. Actually, there is a topic of hot debate in the field yet. So I would say that not the entire community would agree with the same answer. So one possibility is that it takes some time for the 2 neutron star to launch the jet. This seems to be quite unlikely. The other possibility is that the jet forms right away, but it takes some time to break through the material that the merger created. So you have the merger, it comes all together, you form the jet, but it takes some time for the jet to get out. A third explanation that you will find is that we are not looking down to the jet, we are a little bit off axis, and that's the time it takes light to reach your line of sight. So maybe a combination of these three.
Can I add one thing? As a general comment, you know how 5 minutes ago I told you how all these theoretical astrophysicists made predictions and these observations have confirmed them? Well, I kind of lied. Well, the big picture has been confirmed. But this question you just asked, it's a hot debate, is an understatement. The problem is we don't really understand why there was that much of a long delay. 1.7 seconds in these astronomical terms is a very long delay. This is a very hot debated topic, and in fact the observations that Wen-fai and Raffaella are making and through X-rays that are going to come out again behind the sun in next week could give us the answer for why this long delay is coming. But this was not widely predicted. It was an unexpected mystery, so we have some open questions.
There's still time to come back and work with them and figure it out, right?
Yeah.
Other questions? Do you have a question? Yeah, right here.
How many gravitational wave observatories, like is there going to be a maximum number of observatories that will be built? As far as I understand, there are 2 more that are in development. There's going to be 1 in space. But I'm just curious, there's dozens and dozens and dozens of observational observatories. Will there be a maximum, a limit to the number of gravitational waves?
Okay, so let me start by telling you what is happening now. So there are the LIGO detectors, are 2 detectors. One is in Washington State and one is in Louisiana State. And we started, the LIGO observatory started with 2 detectors, and that was the absolute minimum we needed to be certain that we are detecting gravitational waves and not some random noise on the Earth. The way we detect gravitational waves is connected to figuring out that mirrors are being shaped by gravitational waves that are arriving on Earth. But of course, mirrors on Earth can be shaken by all kinds of other things. So having 2 observatories is one of the ways, not the only way, but one of the ways that ensures that it's not some random shaking in one location. So if it's a cosmic signal, it has to have the same characteristics in the 2 locations. And it's not some local random noise. So we needed 2 observatories for this reason. There is a 3rd detector, which is now operating, and we collaborate with the European detector called Virgo in Italy. It's a French, Italian, Spanish, and Dutch collaboration. And the event that was detected 3 days before the binary neutron star, that actually my graduate student Eve Chase led a lot of the work for that binary black hole detection, was the first signal that was seen by 3 detectors. The 3 detectors allows us to localize things better on the sky, which is obviously very important for electromagnetic observations. Yeah. There's a plan, and an active plan, and one of the Northwestern faculty might end up being connected to that. But there's a 3rd detector in India being now under construction. There's a Japanese detector being under construction. So we're talking now 5 detectors. Whether we're going to get more will depend on whether more countries will get involved with gravitational wave astronomy. And of course, it depends on funding. And these are big projects, and what we will need to have is either bigger detectors, underground detectors, and more spread out on the Earth. But what we will also need is to cover the spectrum of gravitational waves the same way we have covered the spectrum of electromagnetic waves. from gamma rays to radio through X-rays, optical, and infrared. And that we can only do if we fly a gravitational wave detector to space, which Shane is particularly involved in. And that will allow us to see gravitational waves from supermassive black hole mergers. That there is no way to detect those gravitational waves on the Earth. Those are very low frequencies, and the whole Earth is basically seismically moving, and there is no way to see those frequencies on the Earth. We have to be in space, just like there's no way to see X-rays on the Earth because the atmosphere is blocking them. So there is a lot of reason and scientific motivation to have more detectors and different detectors.
I think we have one on this side.
Hi, this may be for Professor Fong. I believe you have a fairly large number of gamma ray bursts every year. Is there anything about the characteristics of this gamma ray burst, which is tied to the gravitational wave, that would allow you to identify previous gamma ray bursts and tie them to possible gravitational wave?
Oh, yeah, that's a great question. So, right, so for the past several decades, we've detected lots of gamma ray bursts from these gamma ray satellites, and they've mostly been very bright compared to this gamma ray burst. So, and we think the reason is because basically that movie showed that it launches this collimated jet of gamma rays, kind of like a fire hose of material just pointed directly at us. And so we think that with the gamma ray bursts we've detected in the past, we've been staring straight down the barrel of the jet, and it's been very bright. That's where the gamma ray emission is brightest. Whereas this gamma ray burst, because it was detected by gravitational waves first, that jet of material could be pointed anywhere it doesn't need a very strong gamma ray signal to be detected in gravitational waves. And so this was actually particularly weak it was quite faint compared to these other gamma ray bursts that we've seen. But we were able to see it because it was, one, we had the help with the gravitational wave signal. We were able to look at the gamma ray data more carefully. And two, because it was very, very close. So it was about, I don't know, at least 100 times closer than the closest gamma ray burst that we've ever seen before. So it was extremely close. We were able to see this very weak signal. So this has really mobilized the community to go, the gamma ray community to go back and look and see, have we seen these other little blips before in our data? Maybe they were kind of hidden, weak nearby gamma ray bursts. So that's definitely still an open question in astronomy.
And that's an important point to punctuate, which is these observatories that are tiling the field and taking all of this data keep the images. And so when there's such an event as this, we can go back and look through past data to see if we see that's what she was referring to. Yep. And so there's decades and decades of work that can happen even after the images have been taken, because they're all stored and can be looked at with a new lens once you have new information.
Right.
That's a good point. I think we're going to go this side one more time because I counted over here. Then we'll get back to one on each side.
Zach, there's...
Hi. You mentioned gamma rays and this gamma ray burst. Is that the cutoff? Like, in other words, what about cosmic rays? Are those detectable?
Yeah. So you don't detect the cosmic ray by itself. You detect the shower that it creates. So when the cosmic ray interacts with the atmosphere, it sort of creates a number of charges that we can detect. So yes, definitely yes.
And did we see cosmic ray showers from this event?
No.
Okay.
No.
This side? Do you have people? We're not lining up, so I'm not sure I understand where there are questions. So if you can help us out, that'd be great.
Thank you. Why is it we call them gravity waves as opposed to space-time waves?
Oh.
That's your question, Vicky.
That's my question, yes. So actually, gravity, so we call them gravitational waves and not gravity waves. And gravity waves are more like the waves in the ocean, that of course the gravitational force drives them, but they're not the waves associated with space-time. So gravitational waves could also have been called space-time waves. I agree with you. But for some reason, we stuck with gravitational waves as the terminology. And I'm turning to Shane because he tends to know more of the history of science than I do.
Einstein's first paper was actually called Gravitational Waves in German, if you go look at it. So he's the one who gave it that. The term space-time actually came a little later. This understanding that space and time are together was slow in emerging from the development of relativity. It's largely due to Einstein and Minkowski and Lorentz and people like this. But I think initially, in these early days, there was no standard nomenclature for this. And so, what Einstein said stuck, because he was Einstein, right? And so we just, astronomers are slow to change. There's a lot of things in astronomy we should change that we've never changed, and this may be one of them, so.
Cody, there's one here.
Could you talk just a little bit about the cohesiveness in the astronomy family? You seem to take it for granted, and I just don't understand why and how it works there and it doesn't work elsewhere.
You fooled them well.
I will.
No, I'm teasing.
So I'm happy to take this question. It's not as cohesive as it may appear. But at the same time, science across all science, we realize that it has become bigger and bigger, okay? Science right now is a team sport, I say, okay? And it's no longer one scientist and one student in an office, pencil and paper, okay? That science is long gone. Maybe it still exists in mathematics, but that's about it. So the LIGO scientific collaboration, for example, alone is more than 1,000 people. And it's a challenge in itself. We have been studied by social scientists for how we work and how we actually manage to make progress. And we do make progress. We opened a brand new field in astronomy. And now with this event, we came together, the LIGO scientific collaboration works with the Virgo scientific collaboration, which is in itself 2 separate collaborations. And now these 2 collaborations worked with the electromagnetic community, which is not a cohesive collaboration in itself. It's about, we worked with 70 small teams. Each team was somewhere between 100 people and 5 people. And it was a challenge. And to not acknowledge this, I think, is not fair, okay? It's not all roses, and it was definitely difficult. We published all together close to 4,000 authors, a paper where we told the story of the full discovery, from gravitational waves all the way through the full electromagnetic spectrum. And 11 people wrote that paper in terms of physically, writing every sentence. I was one of the 11 people. But of course, it was written with input from all these 70 teams and the 2 gravitational wave teams and the 2 gamma-ray teams. And I think I grew old 5 years in those 2 months by being on the writing team. But I also learned a lot, both scientifically and as a human. And it made us all better as scientists, and next time we're gonna be better at doing exactly that. And it is a social sport, it's a team sport, and at the end, you know what kept us going? It's the paper we're gonna be proud of. At the end of our lives, it's the paper we're all gonna be proud of. And we kept saying every time we reached the wall, and we had disagreements, and some disagreements were important and some were petty, because we're humans. We're all like the rest of you. And what we said is that we have to write this paper, no matter how difficult it is, to struggle with our egos and how this sentence reflects on me or you, etc. We have to write this paper because this is a historic discovery. And we wrote it through long nights and long fights and lots of smiles. And then at the end, we were all proud of it.
Yeah, it's a good story, good question. I think we have time for 2 more questions. So we'll take one from each side. Who's going where? Go ahead, you pick where you're headed.
Thank you very much. The signal duration of 100 seconds seems very significant. Had it been 25 seconds or 50 seconds, how would things be different?
So the length of the signal tells you something about how massive the 2 objects that are in spiral going one around the other are. So the massive black holes we detected 2 years ago, the length of the signal was only 0.2 seconds, a fraction of a second. But the signal to noise ratio, so how significant, how loud the signal is in our data, can be still very high even if the length of the signal is very short. So the 100 seconds, when we first got the signal and we could tell it was 100 seconds, it told us very quickly we're dealing with neutron stars. But the signal to noise ratio, which tells us how loud is the signal, how important, how bright, in electromagnetic terms, we would say, how bright is this star on the sky, is this source on the sky, it doesn't always correlate with the length of the signal. Now, this particular source, the binary neutron star, was the brightest, the loudest gravitational wave source we had seen, even louder than the very first gravitational wave signal we received back in 2015.
One last question over here somewhere.
Is it possible that gravitational waves contain more complex information? Do they carry complex information about the local area where they came from and also the objects in the way as they travel toward us, such that we might be able to use them to make maps of deep space maps of the sky?
That's a great question. So there's actually 2 parts to your question. So let me first take the first part. Do the gravitational waves carry information about the origin, the local region from where they were produced? So that's very close to where the 2 neutron stars were inspiraling, or the 2 black holes are inspiraling and coming together to form a single black hole. And the answer is yes. So the gravitational waves do carry more information about how distorted the space or space-time was right around the region of the 2 black holes. And we can extract more information depending on how loud the signal is. So it goes back to how the signal to noise ratio question. And so far, we do examine the signal in great detail from this point of view. And we ask the question, is this information imprinted in the waves consistent with what Einstein predicted based on his theory of general relativity? And so far, the answer has been, for all the signals we have detected so far, is that it is exactly the way Einstein predicted space-time should behave, very close, highly disturbed space-time, very close to the 2 black holes or the 2 neutron stars. So no deviations from Einstein's theory. The second part of your question is, does it tell us something about the space between the source and us? And actually there, the answer is not much. And the reason is that gravitational waves have this property of they don't give a damn about what they go through, okay? And that's what makes them so hard to detect. So they don't get impeded, they don't get blocked by anything, and if they don't interact with things along their way. They carry no information about the things along their way. But that's what also makes them hard to detect, because they don't interact much with our detectors. And therefore, it's hard to detect them. So we don't get much information about the space in between.
Thank you. Good question. Well, I hope you've enjoyed this conversation. I think we've learned a lot about the teamwork involved in these discoveries, about the fact that there's still plenty to do, that we are still working on it, and that it can become something that is becoming a routine aspect of astronomy, which is learning more about the universe through these two ways. So join me in thanking our panelists.
Thank you for coming.
Thank you all for coming tonight.